All right, let's get started. Thank you, everyone, for joining this session. My name is Yueping Zhang. I'm Associate Fellow in Verizon. Together with me is my colleague, Sanjay Nayak. He's the director in Verizon as well. So we both are in the SDN technology and planning team in Verizon. So our team, kind of a little bit of a special group in Verizon, which we are kind of very much software-centric. And we serve as a bridge between different organizations, including the device planning, IT organization, operation, engineering. So we provide the feedback and provide the directions on this software planning, covering both wireline and wireless. Today, we want to share with the audience, with the community here, is a journey we had in Verizon to embrace SDN and deploy SDN, and what's our lesson learned, what the challenges we've been facing, and what are our responses to those challenges, and what's the path forward. So agenda-wise, we'll roughly cover those topics. So we start with something called IEN, so Intelligent Edge Network. So IEN we started IEN around 8-9 years ago. It's a greenfield, clean slate deployment of SDN-centric network. So IEN today is a backbone, is foundation of all Verizon services, including wireline, wireless, 5G, so on and so forth. So one of the key components of IEN is an SDN controller called a BNC, base network controller. And we're going to talk about kind of what in the past, like 7 years or 8 years of deployment, kind of what's the benefit what I've been seeing from SDN, what the lessons we learned, and then we'll talk about some growing pain I've been facing, and then kind of what's our responses, and which is the concept of SDN ecosystem, and more in particular, one of the key components called the NEAP, which is a more scalable kind of containerized microservice-based version of the BNC. Finally, we're going to talk about some new initiative I've been driving in Verizon called software-centric planning, and also as one of the initial steps, we call the software SDN as a service. Eventually, we'll kind of wrap up with some concluding thoughts. So this is a slide, very kind of SDN 101. It's very similar to, I think early this morning, there's a keynote from Martin Casado, like 15 years ago, pretty much the same slide, same concept. And so it's, for SDN, among other things, as one of the most kind of fundamental promise was the decoupling. Decoupling of the control and the data plane. And so it's amazing to see this is the true 15 years ago, but it's still true like 15 years later today. And if you look at the figure on the left-hand side from your perspective, it's in the legacy conventional way of managing network. So we have the control plane and data plane are tightly coupled on the network elements. So for network management software to interface with network elements, you have to have an individual interface to each individual network elements from different vendors. And because every vendor have very different interfaces and have different software, so for the management software, you have to build very kind of vendor-specific those APIs. So as a result, it's very complex because we have so many interfaces we need to deal with, and also it's time-consuming because for the same thing, you have to repeatedly to do this from different vendors. And slow innovation. Whenever there's the bug fixes or there's some new feature you need to deploy, you always kind of you have to do the same thing multiple times, and also you're relying on the vendor's product life cycle to make those innovations happen. And last but not least, the vendor lock-in. Right? Once you develop interface to that vendor, very hard to change because everything has been done. It's really you cannot do plug and play. So in contrast, on the figure on the right-hand side, that is the SDN way of doing things. And in the ideal world, we should have a centralized kind of the uniform control plane that is agnostic to different vendors. And the management software only need to interface with one component, which is the control plane. So it doesn't need to worry about what's underlying the vendor device or OS model or even OS versions. We can just do one thing and for all. So as a result, significant costs will be reduced, and also the vendor agnostic those interface will be is a kind of make the business much easier. Yes. Okay. All right. So I mentioned IEN. So this is a kind of a snapshot of IEN in a nutshell. So as mentioned earlier, IEN we started working on this about around 10 years ago, and now it's in production for the past 5 or 6 years. So this is a high-level architecture. So as seen from this architecture, we have 3 layers. So we have on top layer, we have those OSS and BSS there, and also there's different orchestrators such as 5G slicing. Also has a bunch of the functional controllers which do certain kind of network functions such as the path computation or policy or billing, charging. And also have a large pool of automation tools that's being used by IT, by operation, by engineering. And on the bottom, we'll have all kind of network elements from end to end. Start all the way from the RAN, the cell side router, the PON network, the ENSE fabric, the transport, the edge, core, and ultra long haul. Basically everything kind of from end to end, and also everything else in the middle. And sitting in the middle is a SDN controller, we'll call it a base network controller, or BNC. So BNC leverages the OpenDaylight to manage the southbound netcom application connection to the network elements, and also it support the gRPC-based protocols like GNMI, GNXI, GNOI, and so on and so forth. Also, it supports those legacy interfaces, those CLI, TL1, SMP, WebSocket, and the rest. So the main function of BNC is abstraction. So it provides this vendor agnostic northbound API to the different applications, and then they have the vendor specific API to different network elements. So whenever there's a provisioning request come from the northbound applications, so they will invoke this vendor agnostic intent-based northbound API to BNC. So BNC will then translate those API requests to one or multiple those specific API requests to the network elements, so that can make the changes happen. So at the same time, there's tons of data being generated from network elements, such as those alarms, events, performance data. So all the data will be collected by something called Unified Collection Services, or UCS, through gRPC dialogue. And the UCS will sanitize and normalize the data into a more consumable format, and will publish on the message bus. And then based on interest, the northbound application can listen to different topics. For example, the service assurance system will listen to the alarms, and whenever some alarms that require corrective actions, so they will further invoke some API call to those provisioning system, and the provisioning system will invoke the BNC APIs, and the BNC will talk to the network element to make those changes. So basically, this is the way how we make this end-to-end control loop. And also, there's the data will be put in the data lake as well. So there are a lot of tools can do the offline analytics, or to do the archiving business. So BNC, so the IEN has been there for 5 or 6 years, so this is our device count in the past 6 years. So those are all real numbers, but kind of I just sanitized a little bit on the y-axis. So basically, we can see in the past a few years, and we can see that the devices being managed by the Verizon SDN has grown more than 15 times. And then in this figure, we have the bar chart. We have the 2 colors. The blue color means the device is managed by BNC through the direct netcom VN interface. And the orange one means there's some EMS, the vendor element management system kind of in between. And let's look at the blue bar first. So as we can see, those netcom VN devices initially, like 6 years ago, they're very, very little. But now has grown very steadily. But for the orange graph, and we see those EMS devices. So there are 2 messages I want to deliver here. First one, because those are the EMS managed devices are mostly those access devices. So they are large in number by nature. So that's why we see the very high bars. But at the same time, we do see it's still the fact that a lot of devices being managed by EMS, mostly those optical devices or those some proprietary devices which cannot be very easily managed by Netcom VM. But by using EMS, there's a lot of problem we're facing, and Sanjay will talk more a little bit later. But overall, it's actual cost, not only just in terms of paying the EMS, but also whenever the bug fixes or some new features, we need to pay actual cost, and it takes a long time as well. And also the EMS, most time is a black box, really. We don't know what's going on, and it takes a lot of time to diagnose, to troubleshoot, and even fix the problem. So that also causes another kind of layer of failure. So our direction is it's a universal across Verizon, including both wired and wireless. So we don't want EMS. So there's no EMS. So we'll start from the provisioning time flow, the workflow. So we want to get rid of EMS from that workflow first, and gradually we'll remove EMS for other flow as well. So some benefits we see the SDN. I think a lot of points I have touched upon in the previous slide, so I don't want to kind of go line by line. Overall, the benefit we're seeing from SDN is abstraction, uniformity, and its consistency. So we can significantly reduce the integration cost, and improve the provisioning efficiency, especially if we're doing the repetitive configuration on a large number of devices. So this definitely saves a lot of time and effort. Last, but I want to talk about data models. So all the things we're doing in Verizon heavily rely on data models. The data model in terms of not only service model, but also the young model on the network elements. So I've made a lot of effort and come a long way for standardizing the data model with the vendors, which I'm going to talk in the next slide. So this is a kind of evaluation process we started around 5 or 4 years ago. So the goal is to try to work with the vendors to kind of to drive the vendor implementation of the Netcom VM models in a more standardized and uniform way. And to do this, we have five pillars. So the first is Netcom VM. And for this pillar, we're mostly kind of just work on the fundamental implementation of the young model and also implementation of the Netconf following the RFCs. So we'll look at whether they are basically the syntax is correct or not. Are they following the 6241 RFCs? How about the Netconf? Do they support the different error options such as the rollback on errors? How about Netconf monitoring? Stuff like this. And so those requirements will be universal for all kinds of services. So for the next 3 pillars, are more focused on Verizon kind of specific those services. So for Verizon specific, we're looking at three domains: the configuration models, operation models, and the service model. So basically, it's just for configuration model, just for the base configuration, are they doing the job? I mean, do they have the model to support this? And for operation model, it's more talk about those for data operations, such as you want to do a ping, you want to do a trace route, you want to remote upgrade your software or shut down the device, stuff like that. I mean, do they have the proper model to support this? And service model is just kind of very tightly coupled with the Verizon services, such as the layer 3 VPN, E-line, those kind of stuff, to make sure they have a corresponding models being supported. And for the last one, we're focusing on the standard data models. So for the first 4, we really doesn't care about the data model. Either it's a vendor specific or it's a standard. But for the last one, we're really trying to work with the vendor to standardize data model, to follow the SDO data model as much as possible. And to do that, we'll have something called a Verizon Unified Data Model, or VUDN, and which is introduced by different teams to manage this. So basically, the concept of VUDN is largely OpenConfig-based. We use OpenConfig whenever it's possible. But OpenConfig is very fast growing. It's driven by the providers. So its life cycle is much faster for any new changes. But we also do realize there are certain areas that cannot be covered by OpenConfig. So whenever this happens, we'll leverage some other SDU model, such as MEF, BBF. So basically, whenever that's applicable, we'll borrow some wisdom from other kind of organization as well. So here's a chart showing the progress of the vendor data model. I mean, in the past few years, those are real data. I just anonymized those vendor names. But as we can see, by the way, the orange means kind of before we do this maybe the data model kind of standardization process, which may be like 4 years, and the blue bars after maybe like 2 years, just like a 3 year or 2 or 3 year time difference. As you can see, for most vendors, they have gone a long way. It's their data model kind of quality has improved significantly. That's the one exception is vendor 2 here. One of the reason is so Sanjay will explain later. So that vendor is very EMS driven. So as you can imagine, those optical vendors, there are a lot of proprietary implementation. So they are very heavily rely on the EMS. So even though they are migrating away from the EMS, but still the quality of the net compound implementation is still not ideal. All right. So I think that's could be a good segue for Sanjay to talk about the challenge we're facing, especially with the EMS.
All right, thanks, Yueping. The next couple of slides, I'm going to present how we are evolving this SDN usage in IEN network. Before we really get there, right, why to evolve? Like, what are some of the challenges we have? And some of the learning we have from our operational team as well as from the application users. Also, how the complexity of IEN network can be reduced, as we keep adding more networking elements, especially from provisioning perspective. Now, let me start with the challenges we have on the EMS systems today. Here is a simple, workflow of the provisioning through EMS. We have the provisioning apps. They invoke the normalized and abstracted APIs of the controller. In this case, it is BNC. And the controller transforms the ingress payload into egress payload and invoke the REST APIs with the specific template. And EMS picks up the provisioning payload and using the template goes and provisions the networking element. It's a simple workflow. For any type of interface on the southbound side, the same workflow, the protocol will change. Instead of EMS, it could be CLI or netconf. Based on we change the architecture in the controller. Now, when if you see the EMS layer there, we have quite a lot of EMS footprints. You take on the access side or multi-service edge side, core side, or transport side. Every layer we have EMS system for multiple vendors, and they're painful. Now, when we ran into issues, we started looking deep into the EMS system. We started learning about how the architectures are and how complex the architecture is. So generally, our learning there is that the architectures of these EMS systems are very complex and humongous amount of code, layers and layers of code. And pinpointing the exact issue, when we start looking into the log structures are also very weak. Simple functionalities like log rotation, those implementation is not there. So we get lost when you start looking into the logs. And also when BNC invokes those REST calls, there is unpredictable response time, and sometimes the APIs are returned very premature. We have the WebSocket interface with the EMS systems. It's a kind of a streaming, so it's very hard, and the kind of response we get from this WebSocket is very inconsistent. It may not be something to do with the WebSocket, because WebSocket is pretty much a known and stable entity. However, might be it is something to do with how these WebSockets are integrated with the EMS system. And also, when EMS system provisions this the payload into networking element, the challenges there is a lot of syncing issues. Sometimes half configurations are synced. Sometimes we see some ghost circuits in the sense the end-to-end provisioning has not been done. Though EMS, you go and look at the EMS UI, it says there is already a circuit. And also the way the rest is handled on the EMS is very strange. They have job-driven constructs there, where your job is getting scheduled whenever you invoke this REST call. And the scheduling mechanisms are a little bit haphazard. Like sometimes it goes out of order. And so most of these issues we came across as we started debugging into the EMS systems. And we are trying to figure out how we can come up with some solutions in upcoming architecture. The next couple of challenges for us is on the controller side. Our controller architecture today is very tightly coupled in the sense we have some open source component, and above that we have written vertical applications. These vertical applications are tightly coupled with the controller, and they use the resources of the controller. And also there is a closed loop. So whenever there is a new version of the open source controller gets in, it's a challenge for us to go and revamp our application. And it's a huge delivery cycle. And also utilization of those open source we have, we have been integrated with that open source for last might be 4 or 5 years. We might be utilizing only 30% of it. The scalability, high availability and geo-redundancy is the other challenges. Even though we have a geo-redundancy deployed today in the production network, even though we have the controller is on 2 different locations, the failover, failback, connectivity to the device, a lot of manual operation we do, and the suggestions and feedback we are getting from ops is there's a lot more automation needs to be done here. The scaling, Yueping talked about it. The devices are number of devices in IEN networks are growing every quarter, and it's not from one vendor. We have multiple vendors' devices. Also, efficiently addressing that southbound interfaces. We have different type of interfaces from the different vendor, how that southbound architecture can be revamped. On the northbound side, the application interface, the application developers are asking for a lot more standard-based interface, like OpenAPI, for example. Also, the elevated security might be token-based, which I'm going to talk about in the next a couple of slides. The ease of deployment, reducing the release cycles, time, also reducing the development cycle, orchestration, monitoring, and this operational support. Some of these crucial areas we need to improve. No, we looked into these growing, pains. We looked into the challenges we have. We talked a lot with our operational team. We talked a lot with the application developer. Solving these issues, by just re-architecting the controller may not cut it. That's where we thought coming up with an ecosystem might be the right solution. That's where we have a concept of SDN ecosystem. Or on the southbound side, we have networking element from the different vendors. Also, the services provided by different vendor. We have a provisioning platform, NEEP, which I'm going to talk about it in next slide. The NEEP interfaces with these networking elements through model-driven APIs. Even though this is a little bit futuristic, we still have challenges today, as I talked about the EMS systems and CLI-driven provisioning. There are still legacy networking elements out there. The functional control is one more subsystem of this SDN ecosystem, where we bring in mostly path computation engines or topology database, topology managers to assist this NEEP to go ahead and provision end-to-end. Digital device model is one more new area we are exploring in this SDN ecosystem, where Yueping quickly talked about it, where we want to digitize all the young models and provide APIs, so that either the functional controller or the provisioning controller or telemetry, they can use this digital device model. There is also a subsystem of AI/ML platform, where mostly to monitor the end-to-end provision timing, number of APIs, a lot more analytics there. So this is going to be an open architecture, mostly reusable data models, model-driven interfaces, and on the northbound side, intent-based the provisioning. This is where we want to address as a part of the ecosystems. Now, with that, I would like to move on to an important aspect of this architecture is the NEAP. NEAP stands for Network Element Access Platform. It is one of the core component of SDN ecosystem. On the southbound side, we have different interface constructs. They start from netconf, gRPC, CLI TL1, and REST calls, REST interfaces. We model these modules as a stateful set in Kubernetes, where every interface will have two parts, and it has connectivity with the device. Redundant connectivity. I think my time is also getting over here. So the other one is a device mapper, which is responsible for mapping the device, also scaling, and also the device registration process. We have metric service, which collects the analytics and feeds the analytics into device mapper for scaling. Logger service and logger services collects the logs from all the microservices. And the northbound service is for interfacing with the applications. We have around 23 plus homegrown microservices developed, and they're pretty much ready to deploy in production. With that, I would like to hand over to Yueping back. Thank you.
Yeah, thank you, Sanjay. Yeah, for the sake of time, I don't think we'll have time to go too much detail, but I want to share maybe the next 2 or 3 minutes on something new I've been driving in Verizon, something called software-centric planning. And so on the left-hand side, that's the traditional way is platform-centric planning. Kind of everything we do from top down, right? We start from what kind of service we want to deploy. For example, it's 5G or the layer 3 VPN. Then we'll talk about kind of what's the domain that's going to involve. Are going to involve transport, core, ULH, or NSE, so whatever. So we'll pick and choose. And then we can talk about what the network elements will be involved in that domain. And then we can gradually go into more details and what the vendor is going to select, and eventually go to the actual hardware. And finally, at the end, that's when we can start talking about software. But in reality, if you look at those software, those yellow boxes, it turns out for different network the domain like NSE, UT, and MSC, they all end up with one software, the Cisco IOS XR. It's pretty much 90% of the thing we're using across those different domains are the same. It really doesn't make sense to have a very separate those swim lanes who are doing the same thing over and over again. So that's why kind of we're driving to a different paradigm, which is the software-centric planning, which is shown on the right-hand side. So still it's top-down, but the software will be much higher in the layer. And using Cisco as the same example, right? For network, it's network, right? They only do routing and switching. So there are a limited number of those atomic or those modular functions that you need to perform on the network. It's a BGP, it's SS or the RSVP. It means there's only very finite set of those things we need to do. It doesn't matter. We have a it doesn't make sense that we have a very individual kind of those components built for different vendors, different OS, so that we can just instead we have this very normalized and uniform those building blocks that we can reuse for different applications. So this kind of can lead us to the next kind of our more solid step we want to towards this, and is what we call SDN as a service. So SDN service on the left. So this kind of another way to illustrate the figure on the previous slide. So previously, what do we do? What people usually do is we start with either from CLI or from Young model. You come up with what is kind of something we call provisioning guide. Provisioning guide basically is just documentation of the set of APIs or Young model you need to involve for provisioning a device, the service, and all the configured device, and then you have produced this human readable document called sometimes for some vendors it's a Word documentation. And then the development team will kind of translate our work documentation into a more machine kind of readable documentation, such as the Postman. And then until then, we cannot start do any testing. So in the country, in the SDN service, we do things differently. So instead of starting from the CLI, we start with the SDN primitives. Basically, SDN primitive just to set up building blocks I mentioned in the earlier slide, which can be reused by different applications, which is vendor agnostic. Right? But what we do the internal mapping from the vendor agnostic primitive to the vendor specific, the actual kind of YANG model, actual device configurations. And then it's because everything data model driven, so the provisioning guide will automatically generated from YANG model. So in a format such as Postman collection, and this will be the same Postman collection for testing, for development, and for production, for operation as well, which kind of significantly reduces the time and makes everything automated. So for sake of time, I don't want to go to details, but we'll stay here for more minutes for any more questions. But finally, I want to kind of wrap up with some concluding thoughts. So SDN has come a long way since the last 10 years, and we see a significant reduction of the cost and a much better TCO. For data model, we also see very good progress, but we do foresee some challenges, such as vendor native model, standard model, how to reconcile the gaps. There are certain features by nature cannot be covered by the OpenConfig, also standard model, how to deal with that. What's the right way to do deviation? What's the right way to do augmentation? And when and how? So those require a lot of collaboration between the providers, between the vendors, and also the developer community. So we'll foresee in reality that going to be a hybrid environment. We have some vendor native models and the standard models, which require a hybrid, those coexistence of a different paradigm. So the API, how do we handle those conflicts? And how do we handle the risk condition between different data models? So, but in any case, the asset means the fundamental requirements we're pushing, driving with the vendor, atomic, consistent, isolated, and durable. This should be universal rule for any transaction-based systems that are accessing data. Similar kind of as Sanjay mentioned earlier, so this effort and SDN ecosystem effort basically is open collaboration, and we need to kind of consider this presentation as an open invitation to everybody in the community, kind of work with us and try to. If you believe there's something, then you can bridge some gap within Verizon. Kind of we can work together with you. And actually, as a matter of fact, we are kind of actually working with someone in the audience as well on some POC, how to integrate in the Verizon ecosystem. How to bridge the gap, how to prove the feasibility of those solutions. All right, I guess that's pretty much covered all we want to cover. I think we have a couple of minutes for questions, and also we'll be around. Yeah. No more questions. Okay. All right.
I just wanted to ask, there's the TIP and the MUST initiative, and I didn't understand, is the SDN ecosystem what you're doing different from what TIP's trying to do?
Yeah, let's take offline. I got a red flag from there, so yeah, okay. I'll talk to you after. Yeah. Thank you, everybody.